Okay, so if we think back on first semester, uh, we spent quite a bit of time just on power rule, right? We spent a whole unit just on power rule, and then what we learned product, quotient, chain rule. But really, the only derivative rule that we learned was power rule for a long time, and then we started doing natural log derivative, exponential derivative, arc trig, right? And we piled on all the derivative rules once we learned the basics. So for this unit, we're going to see the rest of the integral rules. But the good thing is that these are all just going backwards from the integral from the derivative rules from first semester. So we still have to memorize them, but it's nice to know that we have something to kind of build off of from first semester. So today we're talking about natural log integrals, and I want to show us. Yeah, so these are the two main rules outside of trig and power rule that we need to know. I mean, there are more obscure rules, which we're going to talk about next Monday, but these are the major ones. Just like on the derivative side, natural log derivative is important. Derivative of e to the x is important, so we're going to see that on the integral side as well.
Is there any log function to memorize?
No, the only integral that we have to worry about is log base e, which is natural log. So there's no log base 10 or log base 3 you got to worry about on the integral side. Okay, so let's turn to page 1. So we have integral, let's say we're looking at this problem here, integral of 1 over x dx. What would happen if we attempted to apply power rule to this problem? So let's try that. If we want to do power rule for this, what would need to happen? Where does x have to be if we want to do power rule?
Must be in the numerator.
Numerator, right? So integral of x to the what? -1 dx. Okay, so let's see what happens if we were trying to attempt power rule here. So we add 1 to the exponent divided by the new exponent. So this becomes what? X to the 0 over what? Over 0. Can we divide by 0? No. So this fails, right? Power rule does not work. Right. And actually, this is the only scenario where power rule doesn't work. If it's any other power rule works, right? If it's 1/2 or -1/2, because this is the only scenario that will give us a 0 in the denominator. This is the one case that it doesn't work. So power rule fails. So we have a rule that handles this one case that power rule cannot handle, and that is natural log rule. So it looks like this. The integral of 1 over x dx is natural log absolute value of x plus c. And this one is the u value version of it when there's u substitution. I would say, though, there is a little bit of a warning with this. And the warning is that we're going to see this enough times where we're going to just maybe start assuming that any variable in the denominator is going to be natural log. But is that the case? Okay. What if I had integral of 1 over x squared? This is still what?
Oh.
Still power rule, right? I still want to bring this up to the top and go through power rule, add 1, divide by the new exponent. But what students may experience is that they see that x in the denominator and they may start wanting to do this because they feel like, okay, x is denominator, which means natural log. So I just want to kind of give you a word of warning that we may get so used to this this pattern because we're spending quite a bit of time on it, that we may assume that any variable in the denominator is going to be natural log, which is not the case. Okay, so just remember that if it's x to the or u to the first power in the denominator or x to the first power in the denominator, that's the only case we use natural log. If it's any other variable in the denominator, we bring it up and we go through power rule. Okay.
Only when it's x to 0.
Hmm?
You only do it when it's x to.
We only do it if it's x to the 1 in the denominator. If it's any other power, you bring it up and you got to go through a power rule. Right. Okay, so just to remind us of some of the rules from first semester, the derivative of natural log is u prime over u. And that u prime is really the derivative there. So this is really 1 over u times u prime. And so it makes sense, right? The integral of 1 over u will bring us back to natural log. So there's that connection between derivative and integrals. All right, so let's look at example 1 here. Example 1, can we expand this problem using power rule? What's the issue? Okay, x, and what else? What else about the denominator makes it
+1?
Yeah, there's multiple terms in the denominator. We know as soon as there's multiple terms in the denominator, whether it's added or subtracted and under a square root of multiple terms, we know that we can't expand and rely on power rule. Gotta go through u substitution. Good. So what could be our u value? Say it again. What could be our u value? X squared plus 1. It's going to be the entire denominator. I know we don't see a set of parentheses here, but remember, we want our u value to be a significant portion of the problem. If we let the u value just be x squared, then we're left with u plus 1, and that is still not clean enough. We want a significant portion of the expression to be the u value. Okay, so let's see where that leads us. So if u is x squared plus 1, then du over dx equals what? 2x, okay. Cross multiply. Okay. Dx equals du over 2x. With u substitution, we make our replacements of what we've underlined. And then let's just see where that leads us. All right, what happens here? Anything clean up? The important thing was the x's, right? The 2 was a bonus. It's nice that the 2 also cancels out, but it didn't have to. So then we're left with integral of 1 over u du. Okay. Do we have a rule for this? Yeah. Natural log absolute value of u, right? Okay. U is only a temporary variable, so how do we bring everything back to our answer, or to the answer that we want? Bring back what? Yep. So replace u with okay, so this one, example 2, first off, can we just rely on power rule? We can, right? Because there's natural log in the way. We can't do power rule with that. So we got to go through substitution. If we want to pick a u value, I want to tell us that maybe we have 3 options here, okay? It could be just the x. It could be just natural log of x. It could be x natural log of x. what do you think could be a U value that could end up with the puzzle pieces fitting later on?
Or the exponential of x.
So the issue is if my U value is x natural log of x, what would the derivative of this be? I would have to go through what? Product rule, right? If I went through product rule, it's going to leave me a whole big mess that this problem is not equipped to cancel out, right? So it looks like this is a little bit too much for us to do.
Could we x together and make it x squared?
We can't because this x is inside natural log and this x outside. So these cannot be merged, right? So think about it that way. It's not natural log times x, it's natural log of x. X is inside natural log, it's tough to get to it. What's another option?
Just natural log of x.
Just natural log of x, okay. Looks like that could be a good fit because natural log will produce a derivative and we're hoping that derivative will take out this x that we have there. Now remember, your U value is never just x, right? Your U value is always more than x because the whole idea is you want to make the problem simpler. And if you just do a 1-for-1 substitution, you're not doing much to make it easier. Okay, so here's our U value, natural log of x. What's our derivative for natural log of x? So therefore, 1 over x, right? Cross multiply, solve for dx. Okay, make my substitution. And we can't do calculus steps until the x's go away. Do the x's go away? Yes. And we have a nice clean expression where the rule applies. 1 over u becomes natural log absolute value of u plus c, and then replace the u back in terms of x. So it looks a little bit strange here. Natural log of x plus c. No, we can't. This is inside natural log, is not times, right? This is inside the natural log, so we got to leave it alone. Example 3, I'm going to change this a little bit here. This requires long division, and I'm not going to do long division. I'm going to do something called synthetic division. It's an easier process for something that we can use. So let's do this. X squared plus x plus 1 over x plus 1. Okay, so first off, I want us to realize that can we expand this using power rule? Okay. We can't, right? There's too many terms in the denominator, and also we can't just cancel out across addition and subtraction, right? So we can never do this. We can't just take out the x's. If these are all being multiplied, then we can, but addition, subtraction, we have a lot of restrictions there. U substitution is not going to quite work because the numerator derivative is not going to cancel out below and the bottom is too low. So whenever you have this scenario where you have higher degree with multiple terms and lower degree bottom, it's a little bit of a misfit. We can't quite get a rule to show up. So we have this other method called synthetic division. Now, synthetic division doesn't solve the problem for us. It will not get us to the answer, but it will. The whole purpose is it allows us to rewrite the problem in the form where we can apply the calculus. Yeah, so you've seen this process before, but we're using this process as a way of rewriting the problem. Okay. So the way we do synthetic division is we set the denominator equal to 0. We find the factor for that. So x equals what? -1. Okay, so you're going to put -1 outside a half box. And then you're going to just write down numbers. Okay, do not write any variables, but you're going to write them in descending order. So what's the coefficient in front of x squared? 1. That goes here. What's the coefficient in front of x? Also 1. That goes here. And then the constant is 1. So there's 3 columns here. There's a column for x squared. There's a column for x. There's a column for 1 for the constant. So the first thing you're going to do is you're going to bring the number down below the line. And then you're going to multiply. So -1 times 1 is -1. You're going to add. And then once you're down below the line, you're going to multiply with the factor again. -1 times 0 is 0. Bring this down below the line. Now I want to show you something here. When we're dividing by x, we started with x squared. So when we divide by x, what do you think is going to happen to this degree? Okay, it's going to fall by 1. Okay. So whatever degree you start with, after synthetic division, your new expression is now going to be 1 degree lower. So if this is x, then this is the constant, and this is 1 below the constant, which is the remainder. And the way you represent the remainder is to indicate that I can't divide any further. This is as far as I can go. So this is still unresolved. I still have a 1 over x plus 1 that remains in my expression. So we haven't solved anything, but we've created another version of the problem that we can do the integral for. So now we have the integral of 1x plus 1 over x plus 1 dx. The nice thing is now we have 2 independent problems that we can treat separately. Okay. It's no longer one connected long problem that we gotta worry about. Now these are much simpler problems. The first one we can handle using what? Power rule, right? X becomes what? X squared over 2. Now the 1 over x plus 1 is a little bit of what? We got to go through what for this process? U substitution, right? What do you think the U value is for this x plus 1? Okay, du dx is 1. We solve for dx. Dx equals du. Integral of 1 over u du. No coefficient left over. 1 over u becomes natural log absolute value of u. And then replace the u back with x. Let's see. Okay, and then we said that this portion becomes x squared over 2. Now, once you get more comfortable, if you see something where it's obviously u substitution and it's to the first power and there's no leftover coefficient, then I'm okay if you want to go directly from here to here without writing out the whole u substitution. But if you want to write this out just to help ease your mind that you didn't miss anything, you're welcome to it. But typically, with the easier u substitution problem where you can kind of see towards the end, you can jump from here to here without worrying that, oh, I'm going to take off points because you didn't show me the middle step. So that's up to your comfort level, whether you feel like you want to jump from here to here. If not, then go through u substitution just to convince yourself that you're not missing anything. Okay, let's just Let me show you a few more here. Now we have 6 trig integral rules. There's 4 more that involves natural log, and we have to work towards memorizing them. But right now, let's just practice using them, and then I'll talk about some ways that helps me remember these 4 additional integral trig rules. Okay, so if you look at the top of page 2, look at the top of page 2 here. These are more trig integral rules. Notice that there's integral of tangent, integral of cotangent, integral of secant, integral of cosecant. First, I want to convince you that these rules do not show up in our original list, right? So if we think about our original list of integral rules, right? Integral of cosine, we have integral rule for negative sine. We have a rule for secant squared, cosecant squared, integral rule for secant tangent, integral rule for cosecant cotangent. But we don't have integral rules for these ones, right? And so these are additional ones that involve natural log. So tangent is negative natural log of cosine. Cotangent is natural log of sine. Secant is natural log of secant plus tangent. And cosecant is negative natural log cosecant plus cotangent. So right now, I just want us to kind of practice using them, and then we'll talk about memorizing them. So integral of tangent. Tangent, there's no need for use substitution here. This matches perfectly with this rule here. So integral tangent of x is just negative natural log absolute value of cosine of x plus c. And then integral of cotangent is just what? Natural log absolute value of sine plus c. Now, there is a way to connect between these two. Like, why is there cosine showing up? Why is the sine showing up? The reason why is this. What's another way to represent tangent in terms of sine and cosine? Sine over cosine. Okay, I'm not going to do the whole problem here, but if we let the u value be cosine, then the sine will cancel out, a negative will show up, and that's where that 1 over u shows up. Integral of 1 over u produces that natural log absolute value of u. So the denominator is the u value, and the denominator is what's going to show up at the end of the problem. Yes?
It doesn't. Okay, I lost my.
Okay, it's okay. You can ask later. Cotangent can be thought of as what? Cosine over sine. And so because the denominator is sine, that is why the rule says natural log absolute value of sine. So that is just kind of a memory tool that can kind of help us, especially if we're trying to decide, wait, why is tangent cosine? Why are the rules the way that they are? It's because of the fact that tangent has this relationship, and we can go through use substitution to produce that. Okay, let's do one more synthetic division, and then we can go back to our review. Okay, so we're not going to do long division here, so I'm just going to cross this off and just do synthetic division.
Plus, we're not gonna learn how to do like that percent synthetic.
Yeah, so it's just be synthetic. We're not going to do any long division. Because on the AP exam, we just haven't seen any long division, so I'm just going to do synthetic division. So first off, we realize that there are too many terms in the denominator. We can't expand. We can't do power rule. And the degrees is not favorable, right? Preferably, we want the denominator to be a higher degree than the numerator. So this is a synthetic division. Again, it doesn't solve the problem. It just allows us to separate into easier parts to work with. So if we want to do synthetic division, we set that equal to 0. So what's our factor there? X plus 5 equals 0, x equals -5. So we need do you see anything that is missing from this expression up top? X cubed minus 6x minus 20.
Square.
Yes, missing an x squared. So we need a placeholder for it. So this is really the same thing as x cubed plus 0x minus, 0x squared minus 6x minus 20. If there is a degree that's been skipped over, we need to make sure we have a placeholder for it. So what's the first number we put down? Remember, we only put numbers, no variables, right? So just the coefficient. So 1 followed by 0, -6, -20. Okay. First thing we do is
Bring down the one.
bring down the 1. Bring down the 1, multiply, and add. Multiply, and add. Multiply, there's a little bigger number here. This is -95. And then add. So we started with x cubed, which means dividing by x, we're going to now start with what? X squared. And once you have that first degree established, then everything will just keep falling by 1. So this one will be -5 plus 1 degree lower, x plus the constant,
19.
and then this is the what?
Remainder.
The remainder. And then to represent the remainder, you're going to put the divisor over it to indicate that we can't divide this evenly, so this is the leftover. Remember that we can't just leave this as the answer, right? We haven't solved anything, but we've just made it easier for us to apply integral rules that's available. So make sure that we're only at the halfway point. But the nice thing is that these are all nicely separated, right? I have 4 independent problems, and there's no longer one connected messiness that was hard to work with. So there's 4 terms here. The first 3 I can rely on just what? What rule? Power rule. And the last one, that's a little bit of what? Yeah, use substitution. Okay, so power rule for each of the first 3 terms, x squared becomes x cubed over 3, 5x becomes 19 becomes 19x, and then a little bit of u substitution here. U is x plus 5. D over dx equals 1. A coefficient of 115 stays. Ends up being 115 integral 1 over u, and then 115 natural log absolute value of u, x plus 5. So here's the full u substitution step. But if you're comfortable, you can jump directly from here to here without showing all your u substitution, especially if your u value, if you know your u value is not going to produce anything except a 1, there's no coefficient to keep track of. Okay, let's go to page 3 from your test review. So this is a problem where we're going to build our functions. Page 3. So if you look, G is defined as the antiderivative of F. So G is sitting one level above F. We know that ultimately, eventually, we're going to have to involve G prime and G double prime. Let's go ahead and just build out everything that we need to get the G prime and G double prime. So if G of X is the integral of F of T, then G prime is just the what of that. We're taking the what of this to get the G prime. Derivative, right? So if you see a derivative and integral notation next to each other, you know they're going to cancel out, especially if we're working those processes on the same function. Sorry, X. So these cancel out. This just ends up leaving us with just what? Second theorem, right? F of. This cancels out. What happens next? F of X times 1, right? So just F of X. So G prime is just F of X. So in other words, I'm starting at a level above F. So when I take the derivative, I'm back down to F. So G double prime is just going to be what? F prime. Okay, so we have 3 definitions that we're going to refer back to over and over again between A and F. So then part A says find G of 2. So which definition are we going to refer to? First, second, or third? First one, right? G of X is not asking for G prime, it's not asking for G double prime. So G of X, G of 2, just follow what the rule says. Integral from -2 to what? -2 to 2. So what are we going to do with the graph? Find the what? There you go, right? So just want to make sure that we know what region we're looking at. We're looking at the region between the graph and the x-axis. So just want to highlight these are the places that we're going to be looking at. So I want to make sure that even if we see other shapes in our diagram, that we don't get distracted by them. We're only looking at what's between the graph and the x-axis. So between -2 and 2, we see a semicircle here, right? So 1/2 pi r squared. What's my radius? 2. So 1/2 pi 2 squared, which ends up giving us negative 4/2 is 2 pi below the x-axis. And if I want, I can just split them between the 2 regions here. So the definite integral from -2 to 2 will just be equal to what? -2 pi, right? Okay, G of -4. Use the definition here. Sorry, -2 to -4, my bad. Any adjustment that needs to be made here? Yeah, the bounds are out of order. So if I flip the bounds, what adjustment do I need to make? Change the sign. So if I can find this region, I can make that substitution and replace, make sure I include a -1. Okay, so from -4 to -2, that's just this region here, right? Triangle, 1/2 base times height. This gives us negative of -1. Which is +1. Okay, G of 6. Follow what the rule says from -2 to 6. So -2 to 6, do we need to make any adjustment here? With the bounds? No, that's good, right? So we can just figure out the area of the triangle here, 1/2 base times height. So we add all this together, -2 pi plus 4. Okay, part D, find G prime of 4. So G prime of 4 is just f of 4, right? That's the definition we've established. So what's G prime of 4? What's f of 4 going to be equal to? 2. Next up, G prime of -2. Just the order pair of f of -2. F of -2 is 0. G double prime of 5. G double prime of 5 is defined as f prime of 5. And f prime of 5 is asking for the what at that point? Slope. So if I can find the slope of this line segment, I know the slope of that point. So I'll just pick 2 points that I can find easily and just do rise over run. I can do change in y over change in x, but I think it's easier just to count, right? Down 2 over 2. That's my slope. So what's my slope there? -2 divided by 2 is -1. Okay, part G, for what values of x is G increasing? So G is increasing. We have to create our G prime sign line, right? This is the G prime. This is the G prime graph. We can't just say, okay, this is increasing, that's increasing. This is not the original G graph. This is a G prime graph. So we have to gather our slope information from the G prime graph. So let's label what we're working with here. Above the x-axis is positive slope. Below is negative slope. On the x-axis is slope 0. Okay, for what value is G increasing? Let's create our slope sine line. What are my critical points going to be if this is my derivative graph? Okay. -2, 2, and or just -2 and 2, right? I mean, we already have 6 involved, so just -2 and 2, just the x-intercepts, right? What's the slope behavior from between -4 and -2? Well, the slope is increasing here, but this is really describing negative slope, right? The increasing is telling us about concavity. So it's nice to have these as reminders. That's what we're looking at. Remember, anything below the x-axis are different variations of negative slope. Anything above the x-axis are different variations of positive slope. So look at these guys to help you decide what you're looking at. So, okay, between -2 and 2, decreasing because the arrows are indicating that, right? These are all different variations of negative slope on the original graph. Okay. Between 2 and 6, above, right? So for what values of x is the graph of G increasing? 2 to 6, though. The arrows are really being able to help us, right? Okay, for what value of x is G decreasing? From where? -4 to -2, and then from, yeah, so you could merge it, but I always want to separate just in case something is, yeah, I think it's always a good habit just to go ahead and think about separation, because in some cases you may get points taken off because there's something that is causing these to be, that needs to be separated. Okay, now part I, for find the x values of the points of inflection. So points of inflection, how do I find points of inflection if we're looking at a G prime graph? Max and mins, right? So tell me where the max and mins are. Where do you see the relative max and relative mins on the graph? No, -4 is not. We're looking for hills and valleys. Okay, hills and valleys, peaks and valleys.
0 and 4.
0 is 1, 4 is 1. There's one more. -2. Right, this is a hill of the graph, right? 2 is not it because the graph is rising on both sides. We need the graph to have a peak or have a valley, right? So -2, 0, and 4. Okay. So I'm going to create a G double prime sine line just in case we need more information. And then if we were asking for concavity, what would you say the concavity is between, or the concavity between -4 and -2? Now I can look at the slope, okay? This is now describing concavity. So concave up, concave down, concave up, concave up, concave down. Okay, part J, find the absolute extrema of the function g on the interval from -4 to 6. So now we got to go through what? Yeah, extreme value theorem, which means we're going to test what? Which sign line do we pick this off of? G prime or G double prime? G prime. Okay. So what points do we want to test? Endpoints are critical points. So what points do we want to test? Good. Okay. We don't have to test -2 because why? Is it a relative max or relative min? No. So we can test it. It's just this is no chance. We already know from the beginning it has no chance of being a valid candidate. So that's -4, 2, and 6. Now the nice thing is, do we have this data already from that we've gathered from the problem? Yeah, we have G of 2, we have G of -4, we have G of 6. Now we got to compare these values, right? Which one's the highest, which one's lowest? I know you get to use your calculator, but let's just practice doing this without a calculator, right? Think of pi as what? I know it's 3.14, but easier for us would be just think of it as what? 3. So what's -2 times 3?
-6.
-6, right? That's an easy enough. Don't have to worry about, okay, how do I multiply a decimal through? Okay. What's -2 pi plus 4? It's close enough to what for comparison purposes? -2. And comparing these three numbers, you can tell that the highest is 1, the lowest is -6, or in this case, -2 pi. And so that's how we can write our statement. Okay. The y value is what I care about. The x value is not as important. We can just completely leave the x values out if you want. Just say absolute min is -2 pi, and absolute max is 1. Absolute min is -2 pi. Absolute max is positive.
What's your interval like that?
Oh, this one, because I decided that I was going to test -2, but I didn't have to test -2 at all. Okay, house session tomorrow. Morning, Friday morning. We'll continue to do practice after we get through our notes. Okay. So for your homework, I prefer to just have you guys study for the test. Okay, come get your phones.